van der Waals equations, and non-ideal gas behavior. Let's begin with a quick review of the ideal gas law and how it differs from the van der Waals equation. Within 5% of the normal temperatures and pressures, the behavior of real gases is consistent with the ideal gas equation, PV equals nRT. However, at low temperatures and high pressures, real gases stray from the ideal gas behavior. Therefore, the ideal gas equation is no longer applicable. In 1873, Dutch physicist Johannes van der Waals developed an equation which was relevant to the behavior of real gases over a large range of pressures. The van der Waals equation is a method of calculation used to understand the behavior of real gases by introducing two parameters, constant A and constant B. The ideal gas law's accuracy is compared between the actual volume of 1 mole of gas, also known as its molar volume, Vm, to the molar volume of an ideal gas at the same temperature and pressure. This ratio is also known as the compressibility factor, Z. When Z equals 1, the gas behavior is ideal. However, if Z deviates from 1, the gas behavior is non-ideal. Let's get into the explanation of the origin of the A and B factors in the van der Waals equation in terms of molecular behavior. There were assumptions of the kinetic molecular theory which van der Waals thought were ambiguous, one being that the gas particles occupy a non-significant fraction of the total volume of gas, and the second being that the force of attraction between molecules is zero. The first assumption, gas particles occupy a non-significant fraction of the total volume of gas, is true at pressures close to 1 atmosphere. We understand that the relationship between pressure and volume is, when the pressure increases, the volume decreases. Real gas particles occupy a finite and measurable volume. When the pressure is high, the volume occupied by gas particles is significant, no longer negligible, compared to the volume of the container. Therefore, the volume of gas particles needs to be considered. At high pressures, the volume of a real gas is greater than the calculated volume from the ideal gas equation. The equation which takes into consideration the volume of gas particles is P times V minus MB equals nRT. In this equation, the available volume is represented by V minus NB. B is the constant that is specific to a gas and is defined as B equals to 4 times Avogadro's number times 4 over 3 pi times radius of the molecule to the power of 3. The second assumption, the force of attraction between gas molecules is zero, is true for gases at low temperatures because gas molecules do not particularly have attraction between each other as they are at a far distance from one another. The intermolecular forces between gas particles deviate from ideal behavior at high pressures and low temperatures. When the temperature is low, the kinetic energy that gas particles have is less, making them move at slower speeds. This results in gas particles having a higher chance to interact as they collide. The ideal gas law does not take into account these interactions. When the pressure is high, gas molecules are in close range with each other, causing intermolecular interactions. To take into consideration the intermolecular forces between the gas molecules, the constant A is introduced into the equation. By adding this constant, van der Waals adjusted the slight reduction in pressure caused by gas particles interactions. This image shows how the ideal gas equation changes into the van der Waals equation. The constant A and B are characteristic properties of a gas. Constant A, which is circled, corrects for the intermolecular attraction between the gas particles. The higher the value of A, the higher the intermolecular forces between gas particles, and the more it decreases the pressure of a gas and slowing down the speed at which the molecules move at. Constant B corrects for the excluded volume of gas particles. V is the volume, N is the number of moles, P is the pressure, R is the universal gas constant, T is the absolute temperature. At low pressures and high temperatures, constant A and B are negligible. Therefore, the ideal gas equation is applicable. At high pressures and low temperatures, the van der Waals equation is accurate, and used to calculate non-ideal gas behaviors under these conditions. Now let's try some sample questions involving the van der Waals equation. For sample problem 1, there will be a comparison between the ideal gas equations calculation and the van der Waals equation calculations. Problem 1a states to find the pressure of CO2 in a 22.4 liter container. The given values are: N is 1 mole, R is the universal gas constant, T is 273 Kelvin, and the volume is 22.4 liters. To solve, plug in the values into the ideal gas equation. 1 multiplied with 0.08206 and 273, which equals 22.40238. Divide 22.40238 with 22.4. The pressure is equal to 1 atmosphere. Let's solve the same problem by using the van der Waals equation. The given values are: N is 1 mole, R is the universal gas constant, T is 273 Kelvin, and V is 22.4 liters. The constant A and B for CO2 is found to the table to the left. Beginning with the far right, 3.592 multiplied with 1 to the power of 2 divided by 22.4 to the power of 2 equals around 0.007. 0.04267 multiplied with 1 equals to around 0.04. 22.4 minus 0.04267 is equal to around 22.357. 1 multiplied with 0.08206 and 273 is equal to around 22.4. Now divide each side of the equation by 22.357. Then move 0.007 to the other side of the equation to solve for pressure. Pressure equals to 0.995 atmosphere. When we compare the ideal gas equation and the van der Waals equation at normal temperatures and pressures, the two equations will provide similar results. We went through the details of calculating using the ideal gas law and the van der Waals equation. So let's briefly look at the next two questions to see how the ideal gas law and the van der Waals equations differ from each other when the volume is decreased. For 1b, the volume decreased from 22.4 to 0.2. Then the pressure increases. The force of attraction between the CO2 molecules is strong, which results in a smaller value of pressure calculated by the van der Waals equation compared to the ideal gas equation. When the volume is very small, such as in this question, the pressure is very high, which results in the volume occupied by CO2 molecules being large. Therefore, the pressure value calculated by the van der Waals equation is greater than the value calculated by the ideal gas equation. Let's calculate the temperature of 20 moles of helium in a 10-liter container at 120 atmosphere using the van der Waals equation. N is equal to 20, R is equal to the universal gas constant, P is equal to 120 atmosphere, V is equal to 10 liters. The constant A and B of helium are found in the table to the left. 0.0341 multiplied with 20 to the power of 2 divided by 10 to the power of 2 is equal to 0.1364. 20 multiplied with 0.0237 is equal to 0.474. 20 multiplied with 0.08210 multiplied with t is equal to 1.642 t. 20 plus 0.1364 is equal to 120.1364. 10 minus to 0.474 is equal to 9.526. Multiply 120.1364 with 9.526 equals around 1,144.4. Divide each side by 1.642. The temperature of helium is 697 Kelvin.